Welcome to the tutorial on Serial Adder with Accumulator. In this section, we will design a control circuit for a serial adder with an accumulator. The block diagram for the adder is as shown in the figure. As you can see, there are two shift registers that are being used to hold the 4-bit numbers that are to be added. And in this particular case, we have the shift register which is called as the accumulator and the add-in register. So basically we are going to hold the two 4-bit numbers which are represented as X and Y. So this X register serves as an accumulator and Y register serves as an add-in register. When the addition is completed, the contents of the X register are replaced with the sum of X and Y. The add-in register is connected as a cyclic shift register so that after shifting 4 times, it is back in its original state. So the cyclic shift or the cyclic shift register can be seen here, wherein you can see the way the last bit is made to shift to the first bit. So this way the number Y is not lost because of the cyclic shift. The box at the left end of each shift register shows the inputs SH, which corresponds to the shift signal, and SI corresponds to the serial input. And we also have a clock. When SH is equal to 1 and an active clock edge occurs, when we have SH to be equal to 1, the contents of SI are shifted to X3 in the accumulator and the contents of SI are shifted into Y3 in the add-in register. Also at the same time, the contents of the register are shifted one position to the right. The additional connections that are required for initial loading the X and Y registers and for clearing the carry flip-flop are not shown in this particular block diagram. So if we have to demonstrate the operation of this particular serial adder with accumulator, we can say that at each clock time, one pair of the bits are added. Because the full adder is a combinational circuit, the sum and the carry appear at the full adder output after the propagation delay. When SH is equal to 1, the falling edge shifts the sum into the accumulator and stores the carry bit in the carry flip-flop and rotates the add-in register one place to the right. Because SH is connected to the CE on the flip-flop, the carry is only updated when shifting occurs. So let us look into the operation of the serial adder with accumulator in much detail. So here let me explain you what happens at a time t0. So we are considering that initially all the contents of the accumulator and the add-in register are loaded. We have the full adder and we have the D flip-flop. So initially at time t0, the accumulator will contain X and the add-in register will contain Y. Because the full adder is a combinational circuit, X0, that is this X0 and Y0 and C0, which was initially considered to be equal to 0, will be added independently of the clock to form a sum S0 and the carry C1. when the first falling clock edge occurs, the sum S0 will be shifted into the accumulator and the remaining accumulator digits will be shifted one position to the right. The same clock edge will store C1 into the carry flip-flop and will rotate the addend register towards the right. So the next pair of bits will be X1 and Y1 because we already have S0 which has been shifted in the previous time interval T0. So this next pair of bits which are to be added are X1, Y1 at the full adder input, and the adder will generate the sum S1 and the carry C2. The second falling edge will shift this particular S1 into the accumulator and stores this C2 into the carry flip-flop and cycles the contents of the addend register towards the right. So the bits that we have for the next set would be X2 and Y2. So you can see or observe that in the time interval T2 you have the contents of the accumulator to be S1, S2 and you have the contents to be equal to X3, X2 and the contents of the addend register have been shifted. So at time T2 you are going to add X2 and Y2 at the full adder input and this will produce the sum S2 and the carry C3. This carry C3 will be stored in the carry flip-flop. And in the next step, what happens is that we have the sum that has been moved to the accumulator. So the contents of the accumulator now will be S2, S1, S0 and the contents of the addend registers have been shifted. So during the time interval T3 we will be adding X3 and Y3 along with the carry C3 in the full adder to produce the sum S3 and the carry C4. Hence this is a continuous process until all the bit pairs have been added. So as you can see here, we are having in the accumulator S3, S2, S1 and S0 which is the sum of all the contents of addition that have been produced on adding X and Y and the contents of the addend register have been reset to its original state. So by the end of the time T4 you can observe that the accumulator will contain the sum of the addition. So let me explain the entire process of operation of the serial adder that we have just seen considering a numerical example. So initially let me assume that I am going to have in the accumulator the content to be equal to 0, 1, 0, 1 and the content of the addend register to be equal to 0, 111. So as per my consideration from whatever notations I have considered previously, the accumulator content I am going to denote it as X and the addend register content I'm going to denote it as Y. So at the time t0, as you can observe from this particular table, I am going to see that all the contents will be pushed into the accumulator when SH is equal to 1, that is 0 1 0 will appear in the accumulator, and you can see that Y will be equal to 0 triple 1 when SH is equal to 1 in the addend register. So initially I will be adding the contents in the LSB bit. So if I am going to consider this one to be x0, x1, x2 and this to be x3 and this one to be say y3, y2, y1 and y0. So initially I will be adding 1 with 1, that is x0 will be added with y0, and the value of this particular c0, because initially we do not have anything, so c0 will be equal to 0. So that is why if you can observe from the table, you will be able to see to it that c0 is equal to 0. The sum of the addition, that is 1 plus 1 plus 0, will give you the sum to be equal to 0 and the carry to be equal to 1. So the result of this particular addition, as you can see, will be equal to 0 with a carry C1 to be equal to 1. Now next, when I am going to add, what I will do is I am going to rotate the sum, that is this particular sum that I just obtained, into the accumulator. So the content of the accumulator, this is nothing but S0 that I just obtained. So this is S0. So this S0 will be pushed as an MSB bit into the accumulator, and the contents of the addend register will be shifted by 1 bit. So you can see this is a cyclic shift and the contents will be shifted to 1011. So now I will be adding 0 and 1 of the two registers. So you can see x1 is 0, y1 is 1 and our carry C1 was equal to 1. Again, in this particular case, as you can see, what happens is that we had C1 to be equal to 1. So that is why this C1 will be represented here, and when you add this, the sum again will be equal to 0, and this sum 0 will be denoted as S1. So this is equal to S1 here, and the carry that is generated C2 will be equal to 1, which is been written here in the table. Now next, what happens is at the time interval T2, this particular sum S1 will be shifted to the MSB position in the accumulator. So you can see we are having the content S1 here, this is S0, and this will be X3 and this will be X2. Simultaneously, we are going to have another cyclic shift of the contents of the addend register, so that we are having at this particular time Y2 to be appearing at this point, and we have X2 to be appearing at this particular point. And this one, this carry C2 equal to 1 will appear here. So now you are going to add 1 plus 1 plus 1, which will give you a sum 1 and a carry 1. So you are going to have, on addition of x2 and y2, the sum to be equal to 1 and the carry, that is C3, will be equal to 1. So this sum S2 that you just now obtained, which is equal to 1, will now be moved to the MSB bit in the accumulator, and you have S2 here, S1 here, S0 here, and another cyclic shift of the addend register will yield you Y3 at this particular point, and you have X3 at this particular point. So now you can see X3 is here, Y3 is here, C3 that is equal to 1 is here, and on adding these contents you get the sum to be equal to 1 and the carry C4 will be equal to 0. So what you can observe is that from the table you have the sum, which now I am going to denote it as S3, and the carry is equal to 0. So this sum now is going to be pushed to the MSB bit of the accumulator, and this will be S3, S2, S1, S0, and the cyclic shift of the addend register will reset the contents of the Y register to its original position. So you can see that at time t0 and at time t4 the contents of the register Y is exactly the same. So if you observe, the accumulator will be the one which will be storing the sum of x plus y, and now the contents of the carry will be equal to 0 and the contents of the sum will be the same as whatever the contents that were available previously, that is equal to 1 and 0. So this is one simple example I have considered as to explain how the operation of the serial adder with accumulator occurs. So far in our discussion we have focused only on the addition of the two variables x and y, and then we have seen how we are going to add that using the full adder and how we are going to store that in the D flip-flop and how the shifting occurs, but we have not focused more on the control circuit. So here we have a control circuit for the adder, which must be designed so that after receiving a start signal, the control circuit will put out 4 shift signals and then it will stop. So to understand that in a better way, we are going to look into the state graph for the serial adder controller. So in this particular state graph for the serial adder control, we are going to make use of notations such as ST, which corresponds to the start signal, SH, which corresponds to the shift signal, ST bar, which indicates that ST is equal to 0, that is start signal is equal to 0, and a dash. So initially let me consider that I am in the state S0. So if I am in the state S0 and the start signal is not generated, I will be moving to the same state S0. So hence you can see that in the next state, when ST is equal to 0, if you are in S0 you will move to S0, and if ST is equal to 1, that is a start signal is generated, then you will move from S0 to S1. Simultaneously there is a shift operation that is being initiated, so you can see that the value of SH is going to change from 0 to 1 when you move from S0 to S1. Next, when you are in the state S1, irrespective of the value of the start signal, whether it is 0 or 1, you are going to move from S1 to S2, and simultaneously a shift operation is going to take place, hence the value is equal to 1 1. When you are in the state S2, irrespective of the value of the start signal, you are going to change from S2 to S3 and shift operation is going to occur. That is why you have a 1 1. The same thing applies for the state S3. You are in S3 and you are going to move to S0 irrespective of the start signal, and simultaneously a shift operation is going to occur. So if you observe the state graph, you will note that there is a dash which will indicate that the circuit will continue to shift its position from one state to the other irrespective of the value of the start signal once it has been initiated. So that is why everywhere you can see that once the start signal is equal to 1, after that, irrespective of the value of the start signal, whether it is 0 or 1, it's going to move to the next state. Next, we proceed towards state assignment. Since there are 4 states, we are going to represent them in terms of binary notations, and I'm going to represent them in terms of 2 variables. So 2 variables will lead me to 4 different combinations of the inputs, that is 0 0 0 1 1 0 1 1. In order to fill the next state, I am going to represent the start signal ST as 0 and 1, and S0 I have represented as 0 0, S1 as 0 1, S2 as 1 0, and S3 as 1 1. So you need to fill in the binary representations corresponding to S0, S1, S2, S3 and S0. So that is why you can see that S0 is replaced with 0 0, S1 is replaced with 0 1, S2 is replaced with 1 0, S3 is replaced with 1 1. Now from the state assignment, we can derive the control circuit equations. So I have redrawn the state assignment table here, and I can draw the Karnaugh map and map the various variables and obtain for the flip-flop what should be the equation. So in this particular case, for the control circuit, let me assume that I'll be using a D flip-flop. So I need to make use of 2 D flip-flops in this particular case because there are 2 variables A and B. And I also need to make use of the shift because that is one of the essential parameters, as you can see from the next state table. Now, how do we map the variables onto the Karnaugh map? For that, we need to consider 3 different parameters, that is A, B and ST. ST corresponds to the start signal. So I will have to look into A, B and ST because this parameter corresponds to the start signal when ST is equal to 0 and then ST is equal to 1. So if I have to mark, if you look at DA, I need to look only into the left hand side of the parameters. So 0 0 0, I need to search for logic 1. So you can see that 0 1 0, I have a logic 1, and here 1 0 0, I have a logic 1. Similarly, if I look into this particular ST is equal to 1, I can see that for 0 1 1, I have a logic 1, and 1 0 1, I have a logic 1. Next, coming to the second flip-flop, that is D, B. For that, let me consider the right hand side. So I am looking for the minterm, so I can see that for 1 0 0, I have a logic 1, and here for 0 0 1 and for 1 0 1, I have a logic 1. So now I have completed with 2 of the flip-flops, but I also need to consider the shift. So if I look at the shift signal is 0 only for the first case, rest all it's going to be equal to logic 1. So replacing that, I can see that the shift signal will be equal to the start signal plus A plus B. So this way we can obtain the control circuit equations for all the parameters that we want. And from this we can proceed towards drawing the sequential circuit. Next we have a typical serial processing unit, such as a serial adder with an accumulator, which will process data 1 bit at a time. So if you look at this particular serial processing unit, it makes of 2 shift registers, as you can see, and the output bits from this shift registers will be input to the combinational circuit. The combinational circuit will generate at least one output bit, and this output bit will be fed back as an input to the shift register. When the active clock edge occurs, this bit will be stored in the first bit of the shift register. At the same time, the shift register bits are shifted towards the right. So this is the general serial processing unit, which we have seen in much detail previously. Next would be the control that is present here for the serial processing unit. So this will be very much explained in detail with the help of the state graph. So the control for the serial processing unit will generate a series of shift signals. So when the start signal will be equal to 1, the first shift signal will be generated. If the shift registers have, say, n bits, then a total of n shift signals must be generated, so that you can see from the state graph we have not concluded with just 4 bits. Instead, we have concluded with n bits here. Now, if the start signal is equal to 1 only for one clock time, then the control state graph will stop when it returns to the state S0, which is as shown in the first figure. But however, if the start signal can remain 1 until after the shifting has been completed, that means at this particular point, if the start signal is going to remain 1, then we will require a separate stop state which has been included here before we reach S0. So in this particular case, what it will do is, this stop state will ensure that the control remains in the stop state until the start signal returns back to 0. So this additional stop state would be required if your start signal remains at logic 1 at this particular point, so that you can bring it back to 0 in order to initiate the next set of additional.